All right, so the last subtopic here for chemistry is acids and bases, okay? Now, acids and bases is, we do this because we briefly went over one of the types of chemical reactions is a neutralization reaction. I'm just looking to see if I happen to have a sheet here that's kind of, you can visually look at, but it doesn't matter. Neutralization reaction is when you have an acid and you add it to a base, or a base with an acid, and the products end up being a salt, which is an ionic compound, and water. And I'm just going to go through acids and bases separately, and you'll figure out why it is that they create a salt and water, okay? So an acid. So this is referred to as any substance that has a pH of less than 7 when in an aqueous solution. This may not make sense because you don't know what a pH is, but we are going to get to that at the end of this note, okay? So just remember that acid is anything that's less than 7, okay? Properties of acids. They taste sour, they're corrosive, they react with metals, and when they react with metals, they produce hydrogen gas. So what they do is they release hydrogen ions, so the H+, in a solution, okay? Now, which means acids have to have hydrogen, okay? So they have that positive hydrogen ion. So acids are, examples of acids are, we have acetic acid, which is found in vinegar, and we have our different formulas here. I'm not going to go through them all because some of them are kind of long. Citric acid, which is found in citrus fruits, okay? Carbonic acid, which is found in soft drinks. This one's shorter, it's H2CO3. They all have the aqueous beside it because what it is their aqueous solution. So they're a substance that has been dissolved into a solution, okay? So they're liquids. Hydrochloric acid, which is found in your stomach, and we actually use this hydrochloric acid. We use that one often in the chemistry lab. It's very diluted though, which means that it's very watered down. It's a watered down version. And that's just our formula for that one is HCl. And then our last one here, we have sulfuric acid and nitric acid, which are found in acid rain. Okay, and that's H2SO4 and HNO3. Okay, so those are the different types. Those are some examples of acids. Now, naming acids. All right, so this is another part of that nomenclature. So a binary acid is just a hydrogen plus a single element. I was going to say, for example, hydrochloric acid. It's up here, but it's down here. So, which is just hydrogen plus chlorine, right? And these ones are referred to, they have the hydro in front of it. So for this one, it's hydrogen plus chlorine would be your hydro for the hydrogen, and then you put your chloric, hydrochloric acid. For this one, we have hydro and we have sulfuric, right? Because it's the sulfur, so hydrogen and sulfur. So you just do your hydrosulfuric acid, okay? So the binary is when it's a hydrogen and a single element, okay? So just like our ionic compounds, you have your binary ionic compound, which is sodium chloride, but then we have our other ionic compounds, which is with the polyatomics. Same with these ones, okay? We have our oxyacids, which is a hydrogen and a polyatomic, okay? And these are called ending in ic acid if the name of the ion ends in 8. So like here, this would have been nitrate, right? But instead of the 8, we throw the ic instead. So it's nitric acid, not nitrate acid. So we don't worry about the H, we don't worry about the hydro. It's just that we're taking that polyatomic, right? So this would have been the polyatomic name here, but you're taking the 8 off and you're substituting with ic. Same with this one, right? So that would have been carbonate. I don't know why I can't speak. But instead of that one, we took the 8 off and we stick the ic in there. So now it's carbonic acid. So those are the two types of acids. So you have your hydrogen with a single element, or you have your hydrogen and polyatomic. But what you need to take away from this, because we're not going to do too much naming because this is our last day of chemistry, but what I want you to take away from this is that what the acid is it's giving you a positive hydrogen ion, okay? So it's that ion, okay? It's a positive hydrogen ion. That's what I want you to take away from this. So that's what an acid brings to that neutralization reaction. It brings a positive hydrogen ion, okay? So that's the focus here. That's the big thing that I want you to take away. Then you have your bases. So like I talked about up here, even though you don't know what the pH scale is, and we're going to get to it, acids are anything that's less than 7. Bases are a substance that has a pH greater than 7 when in an aqueous solution, right? So when it's that solution. Don't worry about 7 right now. 7's the middle, it's neutral. Okay? It's neither an acid or a base. So 7's not an acid or a base. 7.1 would be a base. 6.9 would be an acid. 7 is neither, okay? So properties of bases. They're bitter, they're slippery, they're corrosive, they break down proteins, and they release hydroxide ions, which is an OH negative. So acid is a positive ion, base is a negative ion. Acids are a lot of foods, okay? Bases are a lot of like cleaning supplies, like drain cleaner, bleach, okay? So acids tend to be foods. Bases are more like the cleaning supplies. Again, what I want you to take from here, acid is that positive hydrogen ion. A base is that negative hydroxide ion, okay? So examples of bases. We got sodium hydroxide. So it's just sodium with the hydroxide. That's a normal ionic compound, right? That's something you would have named already. A lot of these are, right? Because this is a polyatomic. Hydroxide is a polyatomic. So it's normal ionic compound naming. So we have our calcium hydroxide, aluminum hydroxide, sodium bicarbonate, and then ammonia. This one here, sodium bicarbonate, not one that you would have seen normally. Okay, so naming bases, right? They're using the same rules as ionic compounds. So same thing, it's a polyatomic. Hydroxide, usually it's mostly hydroxide you'll see that's a base. And that is one that you use normal naming for, normal ionic compound naming, right? So you name the positive ion first, which is the metal. Okay, use the name of the polyatomic ion. So in this case, it's that OH, which is your hydroxide. So for example, beryllium hydroxide. Okay, so that's pretty straightforward. Not like the acid naming one. So it's much simpler. All right, so strong and weak bacids. I was combining the names there. Instead of bases and acids, it's bacids. I don't know why I just did that. Anyways, so strong and weak. So acids and bases. So some acids and bases are much stronger and have a higher concentration than others. Okay, some acids we can eat. So here is a scale here of strong acids, weak acids, strong bases, weak bases. And I'm not going to get too much into it, but milk is actually a little acidic. We can drink milk, okay? Hydrochloric acid, that's what's in your stomach and breaks everything down. We can't drink that, okay? It'll kill you. So you see that there's weak acids and strong acids, okay? So, for example, nitric acid is a strong acid, while ammonia is a weak base, okay? How do we measure the strength of an acid or base? Okay, this is what we're talking about when we mention the acid is anything less than 7 of a pH. Base is anything over 7 on the pH. This is our pH scale, okay? Our pH scale runs from 0 to 14. There's nothing lower than 0. There's nothing higher than 14. That is the scale. 0 to 14, that's it. Okay, you're going to do a gizmo on this one too. So this is just kind of a little mini introduction to the pH scale. pH. Right? This is power of hydrogen. All right, that's what the pH stands for. Power of hydrogen. Why? Because acids have that positive hydrogen ion. Bases have the negative, the OH negative ion, but also has that H is hydrogen, right? So they both are carrying these hydrogens, right? So that's what this is all about. Power of hydrogen indicates how acidic or basic an aqueous solution is. All right, so the strength of an acid or a base may be measured by the pH scale. The scale goes from 0 to 14. Neutral solutions are 7. Example of a neutral solution, water. Okay, it's not acidic or it's not basic. Acidic solutions have a pH of less than 7. The closer the pH is to 7, the weaker the acid. Okay, so like I said, here's 7 here, it's neutral, it's water. Milk is very close to 7, very close to neutral, a little acidic, you can still eat it. Tomato, it's 4, that's a little more acidic. Apple is almost at 3, lemon is 2. 0 is the most acidic, and that's your hydrochloric acid. So you see, it's a lot of foods. Whereas on the base side, we have blood, baking soda, which you can cook with, so that's between 8 and 9. Soap, which you wouldn't want to eat. But then all the way up here to 14 is drain cleaner, which again you can't eat drain cleaner. But that's the most basic. Again, so it's very toxic, right? So basic are also referred to as alkaline. So basic or alkaline solutions have a pH of more than 7. So the closer the pH is 7, the weaker the base is, right? The closer it is to that neutral position, the weaker either the acid or the base is. All right, so that's the pH scale. So you're gonna do a gizmo on that. All right, but there's one other thing that we would have done in class, acid-base indicators. So is it possible to test the pH of a solution using indicators? Yes, all right. So we have a few different indicators actually that we tend to use sometimes. I'm just seeing if I have, yes. All right, so I'm going to post this sheet for you guys to use, to fill out. I'm just checking it out. All right, so this is usually something we would have done in class, and I would have had you test out different acids and bases, all right? But we're not in class. So we're going to do it here. So you're going to pull up this chart that you guys have in your notes that I've now posted, and we are going to do some testing. All right, so what an indicator is it's something that scientists have created that they can put in a solution. Oh, that one is a little dirty. Just to find out if it is an acid or a base. All right, so I've got 3 different types of solutions here, and we're going to test them out, okay? So different things that scientists can use, and we would have done this lab in class, right? So there's different types of paper. So there's red litmus paper. I'm just going to pull these out here. There's red litmus paper, all right? And there's blue litmus paper. Now, the difference why we have 2 different colors of litmus paper is because the red and blue litmus paper will change color in either an acid or a base, but it won't change in the other one. So it gives you the chance to test. So if it happens that you put it into an acid and it changes color, and it may have been an accident, you can put the other one in and see if it changes color. So one of these will only change in an acid, and one of these will only change in a base. All right, so you have this sheet, okay? So we're going to do red litmus paper first, and you're going to say if it changes in the acid or the base, okay? So I'm going to put, we're going to do red. So I'm going to put red in each of these ones here. Oh, that one changed pretty good there. All right. So what happened here is this is water. This is vinegar, which is an acid. This is sodium hydroxide, which is a base. So you'll see here the red did not change. It just got wet in the water. It got wet in the acid. It changed to color blue in the base. So you can write that in. The red litmus paper changes to blue in a base. So what we can use these for is that, to test solutions to see if it's acidic or basic. Okay, that's what these are strictly used for, and that's it. That is the only information that these specific papers provide. We have a different paper that we're going to look at that you may have seen before because people tend to use these when testing in pools and stuff. But for these two, the red and blue litmus paper, that's all they're good for, is to test to see if it's an acid or a base. All right, so this is what happens with the red. Okay, now we're going to try, here it says blue litmus paper. Now we're going to try with the blue. Oh, that water's really full, this one. So that is water. That is acid. And that is base. So you'll see for blue, the blue litmus paper changes to red. Let's say it's red. I know it looks more pink, but let's just say it's red because we're dealing with the red litmus paper. It changes to red in an acid. Okay? So red changes blue in a base. Blue changes to red in an acid. Now, that's just the papers that we use in class. There's other things that we use as well as indicators, okay? And that's what these are referred to as indicators, to suggest that it's an acid or a base. T is actually an indicator, suggesting that color that it changes indicates that it's an acid, okay? So there's other things that change color. Cabbage, actually using cabbage juice, and we've done that in class, you can use cabbage juice, it is also an indicator. So this is just to show you that whether or not it's just the simplest way to distinguish between an acid and a base is to use an indicator. That's it. So other things we do use in class are liquids as indicators, all right? So we have a clear liquid here, so phenolphthalein, okay? And this is also something that we use in an acid and a base to tell us whether or not it's an acid or base. So all you're going to do is you're not doing this, I will do it, is we would put drops in the different liquids. So it didn't change color here. So this one is the acid, right? This is the vinegar. Oh, and then there you go. So on your sheets, so you'll see that the phenolphthalein, or phenolphthalein, for some reason I always call it phenolphthalein, but it's phenolphthalein. It changes pink in a base. Okay, so that is something we do use when we are trying to dilute a base to neutral. We'll put it in, and as you would add acid to it, it would eventually neutralize. That's a neutralization, right? When say this is a base right now, we could add acid into it, and it eventually would neutralize it. And then it would all of a sudden, as soon as it's clear, then it was water because it neutralized. Okay, so the last one we would use is bromoethanol blue, is the other liquid we would use. Okay, so just to test it out, this is what it would look like in water. Okay, just goes blue. This is what it would look like in an acid. Okay, and then this is what it would look like in a base. Okay, so it doesn't really change in a base. So it changes yellow in an acid. Okay, but that is another indicator. Okay, so those are our indicators that we would use, just strictly simplest way to test to see if it's an acid or a base. That is all that we would use that for. Okay, perfect. Now, the last thing I'm just going to show you, but you are going to do a gizmo on it, is pH paper, okay? So this is what you would use. You could use it to find out if it's an acid or a base. It'd be more difficult to use this one, but what this one does is it shows you where it is on that pH scale. So remember on the pH scale, it goes from 0 to 14. 0 to like 6.9 is acids, 7.1 to 14 is bases. Well, this paper will change color, and it'll change color to how weak or strong an acid or a base it is, and then you find the color it changed to on this scale. So I'm going to do one really quick, just so you can see how it works. I'll do two actually. I'll test both the acid and the base. And then you guys can do that on, and you're going to do just a gizmo on this one as well. Okay? So, try to put that one back in. So I'll just stick it in here. So this is our base. This is our acid. And what you do, so you put it in, and then you pull the little, I'm going to have to take the whole thing out. Oh, I won't take it out. You can take the little white thing out and pull the card. This is just a card. And then you can match it. Right? So, matching the color, matching this color of the pH paper to whatever color it closely resembles on here. Almost there. That looks like about a 2, right? Which tells us that the vinegar is a 2 on the pH scale. Looks close to 2. Yeah, I'd say it's 2, right? And then our base, trying not to get this. Oh, that's about a 12. There we go. See that? It looks almost like the 12 here. Maybe closer to 13 in between there, right? So it's showing you where it is on the base scale. So that's about a 12 or 13. So that's a pretty strong base. And this is a pretty strong acid. Okay? Oh, look at the little colors it's changing all over there. Very cool. Look at that. Okay. So those are the different types of indicators for the acids and bases. So you guys are going to do a gizmo on pH scale. And then you've got a lab to do on neutralization, and I like that lab, and I wish we were doing it in class because I find it very good. I'm trying to see if I have a copy of it here so I can quickly just talk about it. Yes. So what you're looking at is I give you the information for the sodium hydroxide and the hydrochloric acid, and you guys are going to answer questions on it. Okay, and so really, what would have happened in this lab, and I'm just going to actually go over it with you right now. So this is our acid here. So what you would have done is, technically, you would have had the base. But you know what? I will do here. So this is our base here. So what we would have done in the lab is I'm going to just do a bunch of drops here. Okay, so this is our base, and you know with the base, where did I put the phenolphthalein here would have been, right, that's it, right? It makes it pink. Okay, so it's telling us it's a base, right? So you would have had, tells you, first one it says 10 drops of sodium hydroxide, the other one you would put 25 drops of sodium hydroxide in, and you would have only put like 2 drops of the phenolphthalein in it, but then what you're going to do, sorry, I'm just grabbing, I don't have an acid here, I just have vinegar. What you would have done with your drops of acid is you would have counted out your drops that you would put in here, and you count out your drops until it becomes clear again. Because remember, it is only pink because it's an acid. Because it's a base. So that's telling us that it's a base. But as you add drops of acid, you're neutralizing it. So at some point, it's going to become clear again because it's no longer a base, it's no longer acid, it's just neutral. Okay? And that's what you would have done. See how all of a sudden it's getting clearer? And you would have kept count in. Okay, it's almost at the top there. I don't want it to overkill. But see, I added drops of vinegar, which is acid, and what it did is it neutralized, because remember, the acids provide a hydrogen ion. Your base provides the hydroxide ion. What happens is when you put them together, that hydrogen and that hydroxide come together and they form water. Water is neutral on the pH scale, so it's 7. So that's what we did. We add acid, or the vinegar, until it neutralizes the base. So now you've created some water in there, and then that's where the pink goes away. So that's what the lab would have been. is you would have done it twice. You would have started with your base on both of them. One would have been 10 drops, one would have been 25, and you would have counted to see how many drops it would have taken to you to drop the acid in for the pink to go away and for it to neutralize. I gave you both of those information, but now you know what the lab would have been like, and now you're going to go and you're going to fill out the rest of the lab sheet. Okay? And the other thing is that in the class, you would have taken what you've created here, and you would have boiled it in an evaporating dish, and you would have boiled it until the water was gone. And what would you be left with? There would be something left in the evaporating dish, and that's where you have to think about, you have your acid and your base, like that neutralization reaction, you have your acid and your base, right? And they come together, and what are the two products? You boiled the water out, what are you left with, right? So when you think of your neutralization reaction and your two products, if you boiled the water out, what's the last product? What's the other product you're left with? So think about that when you're writing out your answers on your lab sheet, okay? And then that is everything for today.